Hi, Science 30s. Mr. Riley here. Hope you guys are all doing well. This is our first video for physics. What we're going to be studying in physics is the concept of electromagnetic energy. And our first thing we're going to look at is fields. So our first example of a field is going to be gravitational fields. Even though gravity doesn't have that much to do with electromagnetic energy, it's an example of a field that we're going to look at. So what is a field, first of all? So a field is a region that's around an object in which another object is going to experience a force. So that force could be an attractive force, pulling two things together, or it could be a repulsive force that's pushing two things apart. So what is gravity? And this guy right here is a pretty important figure in the history of science. Is Sir Isaac Newton. He was the first to define what gravity was. And basically what it boils down to, he came up with the universal law of gravity. Basically what that says is that any object that has mass is attracted to any other object that has mass. So there's an attractive force between all objects with mass. And we can add to that a little bit in the context of fields, is that every object with mass is going to produce a gravitational field. And if there's another object with mass in an object's gravitational field, it will experience an attractive force. It will be pulled towards the other mass. So just looking here, I have two masses, and we're going to draw a gravitational field here. And it's actually quite simple. So the way that we draw a gravitational field is we imagine that there was a little, what we would call a test object around my reference object, which would be this. And all we're going to do is, oh no, I touched my face. Don't touch your face, kids. We're going to draw some field lines like this towards the object with mass. And these lines are always going to point towards the object, and they're showing us that this test object out here is going to be attracted to that object there. Now, if I had a big mass relative to, it's big relative to this smaller mass, how I would show that with my field lines is I would just have a lot more field lines pointing to this large mass to show that I have a stronger gravitational field. Okay. All right. Now, how do we measure a gravitational field? So I said that when something is in a field, it's going to experience a force. And you guys know the unit for force, right? It is newtons. That's right, kids. So it's measured in newtons. So if you're experiencing a gravitational field, we measure that in newtons per kilogram. So for each kilogram of mass that an object has, how many newtons of force is it going to experience? Okay, so let's try to calculate the gravitational field strength. Now, here's a question. Calculate the gravitational field strength at the surface of Earth. So it doesn't look like we have been given any information here. So it's going to be a tough problem to solve. First thing I'm going to do is I'm going to go over to this page in my data booklet. And this page is going to tell me a lot of things. Okay, the formula that we're looking at is here. So we have lowercase g. G is the gravitational field strength, and that's the quantity that we're going to be looking for. Uppercase G, or capital G here, is what we call the gravitational constant. So all objects are affected by gravity in the same way. So we're able to construct a constant that can be used to calculate the gravitational force or the gravitational field strength for any objects. And it's this fancy number right here, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. The M is our mass, and our mass here is going to always be measured for us in kilograms. And then we have this R here. Now, R is basically distance. It's separation distance between two objects. And so we're looking at we're going to look at the surface of Earth here. So I'll explain how to use that. So sometimes it's explained as radius, and I'll explain to that why. So let's go over here and look at our question again. So for Earth, we have the Earth here. So let's say this is Earth. Here's the center of Earth, and this would be the radius of Earth. And we want to know, what is the field strength right there? So I need to get a little bit more information. And luckily for me, I have a data booklet. And in my data booklet, I'm going to find a few things. I'm going to find the mass of Earth, and I'm going to find the radius of Earth. And if I have those two things, I'm going to be able to calculate the gravitational field strength on the surface of Earth. And so let's do that. Okay, so I have the mass of Earth, which is 5.98 times 10 to the 24 kilograms. Yes, Earth is big. I have the radius of Earth, or the separation distance between the center of the Earth and where I want to measure the field strength. And that is 6.37 times 10 to the 6 meters. And then I also have capital G. That's a constant. That's going to be the same every time you're using this formula. So it's 6. What is it again? I can never remember. Oh yeah, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And then G, little g, that's your gravitational field strength. That's what we're going to be looking for. I am not going to ask you guys to manipulate this formula just for the online course. You're always going to be solving for little g. So that's kind of nice. So really, we just got to plug and play. So I have 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And then I have M, which is 5.98 times 10 to the 24 kilograms. And then on the bottom of this formula, I'm going to have R squared. So that's 6.37 times 10 to the 6 meters. So some of you guys might be wondering, why did I put that kilogram squared on the bottom here? Because the unit for this constant is Newton meters squared per kilogram squared. So that's why I put kilogram squared on the bottom. And then what we can do is we can actually cancel out some of the units here. So I have kilograms up here. So I'm going to get rid of one of these kilograms down here so I can get rid of that squared. I